Section 6.2. If you've taken physics before, then you know that sometimes you want to be able to write a vector as the sum of two other vectors pointing in different directions. Now, if those directions happen to be orthogonal, we call that an orthogonal decomposition. And that's what we're after today. So first, let's talk about orthogonal sets and orthonormal sets. A set is orthogonal if the members are pairwise orthogonal, and that means that every u dots to 0 with every other u. And further, if those u's all have length 1, then we say that set is orthonormal. And we can apply those definitions to bases too. We can talk about an orthogonal basis or an orthonormal basis. So for example, let's show that this set consisting of three vectors is orthogonal. So we have to show for part A that three things happen. One, u1 dot u2 should be 0. So let's just check that. We get 1 minus 1. Yes, that's 0. u1 dot u3 should be 0. Yes, just doing a mental check. And then finally, u2 dot u3 should be 0. And indeed, that is 0 also. Now, since dot is commutative, then that's all we have to show. Those three dots are equal to 0. All right, so that's an orthogonal set. Let's transform it into an orthonormal set. So for B, we want each vector to have length 1. So we want to take u1 and divide out by its length, take u2 and divide out by its length, and u3 and divide out by its length. All right, well, let's look at the length of u1. That's the square root of 1 squared plus negative 1 squared plus 0 squared, which is root 2. So our first vector, u1 over the length of u1, will be 1 over root 2, negative 1 over root 2, 0. The length of u2, we can see, is also root 2. So we divide out by root 2, 1 over root 2, 1 over root 2, 0. And then finally, u3 already has length 1, so we divide out by its length and we just get u3 again. So that's an orthonormal set. Now, Theorem 4 says that orthogonal sets of non-zero vectors are linearly independent. Now, we know that whenever a set has the 0 vector in it, it's linearly dependent. So we have to assume we have all non-zero vectors, but the fact that they're orthogonal gives us linearly independent. And I've got a proof of that at the end. I also have a proof of Theorem 5. So Theorem 5 tells us that if we have an orthogonal basis for a subspace W, each Y in W can be written uniquely in this fashion. Now, this formula is one that you're going to want to memorize. I know it looks kind of ugly, but you're going to use it enough to want to memorize it. And a corollary is that if that basis is not only orthogonal, but it's orthonormal, then the formula becomes even nicer. It simplifies to this. Now, the reason for that is the only difference in these two formulas is in the top one, you're dividing out by u1 dot u1, u2 dot u2, etc. Well, if the length of each u is 1, then those denominators all become 1, and that's why you're not seeing them in the second formula. All right, so let's see what this is good for. Suppose we have a vector y here, and we want to write it as a linear combination of the orthogonal basis u1, u2, u3, and we've already checked that that's orthogonal. So by Theorem 5, here's the formula we want to use. Just to shorten the video, I already wrote down the formula. So this is, let's just start computing dots. Y dot u1 is going to be negative 4, and then I take u1 dot u1, that's going to be 2, u1, and then plus y dot u2, 7 plus 3 is 10 over 2 u2, plus y dot u3, just visual inspection here, that's a 4 over 1, that's u3, and so that's equal to negative 2 u1 plus 5 u2 plus 4 u3. Okay, now that was pretty quick. The old way, if we had to do this in the past, what we would have done is we would have reduced the augmented matrix u1, u2, u3, augmented with y, and we'd have gone down, reduced, and we would have gotten the weights in the linear combination, and the weights would have been negative 2, 5, and 4. So that was a real time saver. Okay, why don't you try it? right? Y is a linear combination of these two vectors. And I'm switching up the notation here. I'm going to write these vectors in linear format. Okay, hopefully you did that. The formula you want to use, the more times you write it down, the easier it will be to remember. Y dot U1, U1 dot U1, U1 plus Y dot U2, U2 dot U2, U2. I'm using the same formula that I used above, except I only have a U1 and a U2. Okay, Y dot U1 is going to be 26. U1 dot U1 is 13, and that's U1 plus Y dot U2, let's see, that's negative 52. U2 dot U2 is 52, U2, so Y is equal to 2 U1 minus U2. And I was able to do it that quickly because I was told that these two vectors were orthogonal, but I could have done a quick check. 12 minus 12 is 0, so yes, they are orthogonal. All right, so now let's start talking about the orthogonal decomposition. Suppose Y is negative 3, 4, that's this red arrow here, and U is negative 2, 1. We can write Y as the sum of a vector in the direction of U and perpendicular to U. So we can decompose Y. And this is the decomposition here. And let's just check some things. Is this really equal to Y? So let's add these two vectors together. We get negative 3, 4. Yes, that's Y. And is Y hat, which is negative 4, 2, parallel to U? Well, negative 4, 2 is equal to 2 times negative 2, 1. And so Y hat is a scalar multiple of U, so that means it's parallel to U. And then to check that Z and Y hat are perpendicular, we need to check that Y hat dot Z is 0. So here's Y hat, here's Z, so we get negative 4 plus 4 is 0. So yes, those are orthogonal. So in my picture, my Y hat and my Z are orthogonal. Okay. So that illustrates some definitions and formulas I have here in this box. For any U in Rn, if L is the span of U, so L is some line spanned by U, the orthogonal projection of Y onto L is Y hat, and it's this formula here, Y dot U over U dot U, U, and we can write Y as the sum of Y hat plus Z, and Z is just the difference between Y and Y hat. And that when we write Y like that, that's called the orthogonal decomposition. And in my picture here, this arrow here is my Y hat, and over here I have my Z, and you can see that the length of Z gives me the distance from the tip of Y to the line L. And we'll formalize that, the fact that that is the distance, in the next section. Okay, so let's try it out with a concrete example. We're given a Y, a U, and an L. L is the span of U. Let's find the projection of Y onto the line L. So Y hat, again, write down the formula, and I hope you remember it. Y dot U over U dot U, U. Now Y dot U is negative 24 plus 4, so negative 20. U dot U is 10, U. So that's negative 2U, and I'm going to write U in linear format, 3, 1. Just a good space saver in this whole chapter. We're going to start to transition over to this format. So this is negative 6, negative 2. And then write Y as the sum of two vectors, one parallel to U. Now that's going to be my Y hat, and one orthogonal to U. That will be my Z. So first I need Z. Now Z is just the difference between Y and Y hat, okay? Y is negative 8, 4, and Y hat, we just computed, is negative 6, negative 2. So that's negative 2, 6. So Y is equal to Y hat plus Z. Y hat is negative 6, negative 2. And then I add on Z, which I just computed, is negative 2, 6. So this is my Y hat again, and this is my Z. So there's my decomposition, and it's an orthogonal decomposition. So let's do a safety check. There are two things to check. One, is Y really equal to Y hat plus Z? So just add those two vectors together, and let's see, we get negative 8, 4. Yes, that indeed is Y. And 2, is Y hat dot Z equal to 0 because we want those two vectors to be orthogonal. So y hat dot z is equal to 12 minus 12, which is 0. So that's a check too. And so in my picture here, I've got y and I've got u. This dotted line is L. So when I project y down onto L, this vector here is y hat. And the difference between y and y hat is this vector here, which is z. And the length of z will give me the distance from y to L. So in part C, I want the length of z, which is simply the square root of -2 squared plus 6 squared, which will give me the square root of 40. All right, in the next section, we're going to generalize this orthogonal decomposition, not only to a line L, but a whole subspace W. So I'm going to finish with a talk about orthogonal matrices, and you don't have to memorize any of this, but I do want to talk about it just a little bit. There's a lot going on here. Let's start with Theorem 6. An m by n matrix has orthonormal columns if and only if the matrix transpose times the matrix gives you the identity. So U transpose times U is the identity. And that's fairly easy to show. Theorem 7, U is an m by n matrix with orthonormal columns. So we can think of U as a mapping from Rn to Rm, and it's got orthonormal columns. If that's the case, then three things happen. U preserves length. And remember, that's pretty interesting because X is in Rn, Ux is in Rm. Those vectors might be in completely different dimensions, and yet they have the same length. U preserves angles, and U preserves orthogonality. So an example of that, which we'll see on the next page, is a rotational matrix. When you rotate two vectors, it doesn't change the angle between them. It doesn't change their length. And if two vectors are orthogonal, they stay orthogonal. Okay, and here's another definition. If a matrix is square, it's orthogonal if its transpose is equal to its inverse. And you can show that if a matrix is square and it's got orthonormal columns, remember if it's got orthonormal columns, then U transpose U is the identity. That implies it's orthogonal. And the reason for that is by the IMT, we know if U transpose U is the identity, then U transpose is U inverse. So let me just end with an example of these things. The matrix A here, corresponding to a rotation by pi over 2 radians, is orthogonal. Now I can show that one of two ways. One, I can compute A transpose. All right, so that's 0, -1, and then 1, 0. And then I can show that's equal to A inverse. So let's compute A inverse using dancing naked bears. A inverse would be 1 over the determinant of A, which is 1. And then I switch the zeros, those stay 0, and I make B and C negative. So this is 1 and this is -1. And that's 0, 1, -1, 0. And indeed, that is equal to A transpose. Okay, so that's just the definition. Or I could use this fact here. I've got a square matrix. I know it's going to be orthogonal if its columns are orthonormal. So A is square and has orthonormal columns. Let's just do a check of that. Here are the columns of A. Yes, they both have length 1. And if I dot those two columns together, I get 0. So we have orthonormal columns. So you could show that A is an orthogonal matrix in one of two ways. All right, and that is the end of this section.